We're now going to move on to start thinking about supervised learning algorithms. And supervised learning algorithms start with this premise that I give you data and I give you labels for that data. So the supervision comes from the fact that I'm going to give you directly information about that data set. And so this is kind of the structure of supervised learning, is to actually inform yourself about what you're doing. You actually have knowledge about that data set, which you are exploiting in terms of coming to the data and using that information in order to build models directly from that data. What I'm going to show you here for this supervised learning algorithms is going to be just really related again to classification and clustering algorithms. Okay, so the first thing I want to talk about in terms of supervised learning is a classic method, more than 100 years old, what's known as linear discriminants. And so the basic of trying to understand what a linear discriminant is just think about taking your data, and when you think about two sets of data, or two clusters, is drawing a line between those two data sets. What is the best line separating the data? If I have cats and dog images, and in some feature space I get clustering, where do I draw a line between the dogs and cats to optimally separate them in terms of a classification task? That's what linear discriminants is after. And so these linear discriminants aren't just lines, but generalization of lines. In other words, hyperplanes. How do I cut the data to best separate the classes that I have, or the labels that I have? So this is what this algorithm is about. It's a classic algorithm used extensively in data science. So let's first draw the picture of it. A picture often tells 1,000 words, and in fact we go right back to dogs and cats examples in some feature space and principal component space, which might look like this here, which is actually a data set that was used. I talked about it in the first set of lectures on this, which was I have 80 dog pictures, 80 cat pictures. I look at their low rank representation in terms of principal components. And what you're seeing here is the magenta are the dogs, the cats are the green balls. And so right away you could see that there seems to be sort of a separation between the dogs and the cats, right? So one way to think about it is if you were to draw the best line, somehow it would be somewhere in here, right? Something that would separate the dogs from the cats. The question is, how do you mathematically go after that? So at the end of the day, again, what data science really is concerned with is taking a conceptual piece, which is trying to separate this data, and writing down a mathematical architecture that does exactly that. And the way we're going to do it through linear discriminant is by taking this data and basically projecting it into a line where we can do the discrimination. What line should I use? Well, I'm giving you two projections here onto a line. The first one is this one right here, where I could take the purple balls and project sort of in some sense their distribution along that line. And you can see that's this purple distribution here. And if I was using this line, I could also project the green balls or the cats onto that line. And you can see that there's a huge overlap between the purple and the green. In other words, it's very hard on this line, in this direction essentially of, let's call it feature space, to make a distinction between what are dogs and what are cats, because their statistical distributions basically overlap. And so this is problematic, and it's a terrible direction in which to sort of do this classification task. However, there's a different line. Let's say this one here, that if I project those purple balls and those green balls onto it, you get something more like this. Notice how the purple now and the green are very well separated. There's still some overlap, their tails overlap, but in the end, if I were to draw a discrimination line along this line right here, in fact, right about this point, I would very nicely separate the dogs from the cat. So this is sort of your optimal projection versus this is a very poor projection into a way of doing discrimination. So the idea of a linear discriminant analysis is pretty simple. How do I find this projection? How do I best find that line so that if I take my data, its distribution, and I project down into something like this line where I'm trying to separate these two, that I get a very nice separation of the data in general. Of course, these look like, this data looks like it's Gaussian distributed. It doesn't have to be Gaussian distributed, but once you have it down into that space, then making a decision or a classification on that data becomes very simple. Again, this is historically one of the oldest techniques out there from the early 1900s from Fisher. And so this discriminant analysis is really important and is sort of a building blocks, just like principal components are in terms of a baseline model to see how well you're doing with a discrimination task. So let's think about the architecture of this. So the first thing I want to point out are a few key features. One is, if we look at the data, remember I have labels for the data. So I would know what the magenta balls are. I also know what the green balls are. This is very different than unsupervised learning, which I don't even have those labels. But since I have those, I can actually, for my purple balls, my dogs, I can do things like ask the following question. What's the mean and variance of my purple balls? What's the mean and variance of my green balls? And these are going to be the kind of things I'm asking when I do this discrimination analysis, because the mean and variance are really what are dictating what's going on down here in terms of these distributions right here. So we're going to look up here, we're going to look down here and sort of think about the mean and variance are going to be critical in terms of building this discriminant analysis. So here's how the formal optimization architecture looks like. It's basically going to be a projection onto this best discriminant direction. And the calculation is to basically, if you look here, this is going to be looking along this direction that we have, where it's a projection where you're projecting onto what's called the SW and SU. And this is the between class and in class variance. Those are what those matrices are. So what are these objects? Well, between class is if I have the distribution or the variance, and this is a variance metric right here. So this is the square of the difference of the means. So essentially looking at the mean of mu1, mu2, which are the two data points, and you're squaring this. So it's sort of in some sense looking at the between class variance. So you want that to be as big as possible, right? So you want to have a direction in which those two points are as far away as possible. Let me go back and show the picture again. So in other words, what that's actually saying, coming back to this picture, is basically wherever this mean is and the distance to that mean, I want that to be as big as possible. You can clearly see in this direction here that those two are very close to each other. The means of the purple and the mean of the green in this projection is not very good. Those are not well separated. So, however, here, look how far away the mean of the blue, magenta, and the mean of the green are. They're very well separated. So I want to maximize that. Okay, so that's what, let's go back here. That's what this is doing here. So that's what the top is. I'm going to try to maximize the distance between where the means of those two distributions are. And on the bottom is I'd like to make the distribution, the variance, the in-class data. So in other words, if I'm in the magenta, I'd like to have as small a variance as possible. Same thing with I like as small a variance in the cats and dogs as possible. So in other words, I want this to be as small as possible. So I want to make this sort of going towards a divide by 0. So this is going to make this as big. Okay, so this is big on top, small on the bottom. So that's one way to think about it. And again, going back to the picture we had here, here we go, sorry. Clicker doesn't work so well, but here we go. Here we go. There we go. So when we look at this here, what I like to do is for the mean of the magenta and green to be as far away as possible, and for essentially the variance of each to be as tight as possible. So if they're well separated with very tight variance, that means I can very easily discriminate between them. That is what this optimization is actually looking for. Try to take your centers to a projection, and when I look at these projection spaces, try to make it so the means are separated, the variances are tight. That's going to give me something like this, which will be the optimal. So that is the optimization problem we are looking at here. And again, this is how you would do it. This is what you're looking at overall. W that maximize this, right? So this is the arg max of this thing. So what is this quantity that maximizes this? And it turns out this is related to solving a Rayleigh quotient, an eigenvalue problem, essentially, which is given right by here. So this is a very nice technique where you're using information about the distributions, the variances, and the means, and maximizing it so that the projection, and the projection now is found by an eigenvalue problem, gives you, in fact, your discriminant line that best separates the data, at least from the metrics we use, which is make the means far apart, the variances tight. Okay? So that's how you would solve this. So it's a very standard method. It goes back a long time, and it allows us then to solve this problem. And so we can start getting things like the following here, which is this is what this looks like. If we're now in the dog-cat space, I just showed you this. So essentially it's drawing this line here. This is the best line of separation. So along this line, the projection, which is essentially orthogonal to this, right? So the projector is sitting across here where I drop the distribution onto. This line here is the best in terms of separating out the data between the dogs and the cats. This is a linear discriminant analysis. You can do something very similar to this, related to this, which is called quadratic discriminant analysis. So instead of fitting a line, I can fit a parabola through there, which would look something like this. So these are all options available to you in terms of these discriminant analysis techniques, which allow you to take data and start to separate them. It's all based on the fact that you have labels. And the fact that you have labels allow you then to compute the in-between class and between class variances in order to produce these lines. So really critical is that you actually have the training labels associated with it. So you already know what the magenta and green balls are. Now, once you've trained this model on the data, now you have a classifier. So if you have a new picture of a dog and a cat, for instance, you would bring this in, you would project into PCA space, see where it ends up in this space, and if it's over across this side of the line, you'd say that's a cat, and if it's on this side of the line, it's a dog. So these are how these classifiers work. You train them on some base set of data, and then you deploy them in a real-world function. Now remember, we have this issue of D prime D. D prime is your actual data you trained on, as D is the real world. And you can see that even with this training here, you clearly see you make mistakes. Some dogs are classified as cats, and some cats are classified as dogs. So that is an issue. There are, in fact, one of the key features, if you look at some of the features here, is that the dogs that have triangular ears, all the cats have triangular ears, and that's one of the principal components that comes out of this. And so if there's a dog with triangular ears, so, you know, like a lab has floppy ears, but there are Pomeranians, for instance, that have triangular ears, and those triangular ears make it very easy for this thing to classify your dog as a cat. Okay. All right, back in here. So this just finishes up this example. This is sort of a classic technique used quite a bit based upon, you know, simple mathematics of eigenvectors and of matrices, and these matrices are the between class and between in-class and between-class data sets of variance. And so you can build these discriminators, which is an old-time technique that's been around for quite a long time. And so this is just a very classic method. It's not used heavily in a lot of machine learning literature because it's fairly restrictive, but it's highly interpretable. So that's one of the advantages you have of this classification lines. If you can build a linear classifier like this, you can actually go then and apply it and have a very interpretable line, and even look at this between class, out of class variance, and be able to do things quite nicely with it. What we're actually going to build next towards are, let's say, more commonly used machine learning techniques that were dominant before the rise of neural networks. So let's say pre-2014, what you had is machine learning revolving, especially around classification and supervised learning, revolving around two key technologies. One is what's called support vector machine, the other one is classification trees. So we're going to delve into those, which give you less interpretability. The mathematical architecture is a much heavier lift. However, it gives you, in general, much more robust performance than this simple technique here of the linear discriminants.